So 1.2 is just about basically solving for C, the constant. You know, you guys remember when you would integrate and you'd have a C, right? So solving for that C is the initial value problem. So you may have seen that in Cal 1. They touched on it just a little bit. They like introduced differential equations and then they never touch it again. They just move on because there's a whole class on it. So anyway, so we're going to touch on those ideas and go from there. Okay. Let's find a good example. All right, let's say it's example 1. Solve the, let me turn the lamp on. Is that better or worse? Is that okay? Just let me know if I'm ever out of focus or something. Okay. Also, a thumbs up is cool for responses. All right, solve the initial value problem. Also called IVP. So I'll probably use IVP after this just to save time. So if they give you, let's say, they say y is equal to CEX y prime is equal to y, and we're given this initial condition y of 0 is equal to 3. So usually you don't know the solution, but usually all you're given is this, right? And then you try to solve for it. But you can kind of deduce that if you take a derivative and it stays the same as the original y, then it's most likely going to be e to the x, right? It's one of the only functions that do that. So if the derivative is the same as the original, well, we're probably talking about this. So I'm going to go ahead and give it to you. Now, given this initial value, we're saying that at y0, we have 3. So this could be, so eventually, right, these types of equations, differential equations will be determined by some real life temperature, time, whatever. So that'll help you solve and giving you a specific function. Because right now, C can be anything. So it's really like a family of solutions. Okay, so visually, right? Let me open that up. So visually, if y equal to c to the x is a family of solutions, let's say one can, I mean, c can be anything, right? So we don't use whole number just to keep it simple. So if this is the original, and copy paste this, let's say there's a 2, right? Say there's a 3, there's a 4, right? Or there could be a -1, a -2, 3, -4. So basically, eventually we're going to talk about is fields. That's like more of a solution. Let me see if I can find a good picture for you. It might be in 2-3 though, or 1-3, so we might just wait on it. But basically, what I was just trying thinking about is that it's 2-1, so that's coming up in a little bit. So it's like a preview of 2.1. So the initial condition, which like I said, could be temperature, could be position, could be whatever, initial velocity, something, right? You're gonna have like a huge, I guess think of it as like a field like of currents. So picture this plane full of a bunch of arrows going in different directions, just like a turbulent water where you have the forces going all over the place, right? They're not uniform really. Maybe a bunch going in some direction because water flows in a certain direction, but if it's churning like crazy, if it's hitting rocks, you have water going all over the place, right? Different directions. It's called a directional field. So you can picture putting a little boat in some of those spots, and then it'll start going into those paths, right? So if I give an initial condition of 0-3, then it's going to be that purple one. Right? I'm going to go in this path. So we're going to solve for that in just a moment. So that's why the IVP is important, and because it gives a specific solution, which we're going to be talking about quite a bit anyway, also, all the time. So here we go. So plug in 0. So y of 0 means you plug in 0 for the x, right? And it's equal to 3. So that implies that c e to the 0 is 1, so c is equal to 3. So our actual solution would be 3ex. So that's what I'm talking about. It turns out to be the purple one. Okay. That makes sense? Let's suppose we just change up the initial condition just for fun, right? Let's suppose y of 1 is equal to -2. So now that's going to change the path, right? The path that this function will take. So out of the family of infinite solutions, this will give me one of them, a unique solution. Okay. So y of 1 is equal to ce to the -2, which is equal to, 1, not 2. 1 equal -2. So that implies that c is equal to -2 over e. So our equation this time, our solution, this is the first part 1 here. I'm going to call this part A, so it's a little neater. Part B. Put B over here. Okay, so the solution will be y equals 2 -2 over e times e to the x. Do you guys see a way to simplify this further?
Would it be -2 e to the x minus 1?
Yeah, that works. E to the x minus 1. That's as pretty as it's going to get. There's our nice back of the book answer, right? And if you ever feel confused by an algebra step I skip, just let me know. I'm trying not to, but I might skip some here and there. Just let me know if you want to see more steps. No big deal. Anyway, so any questions on this idea? Does the idea make sense? Okay. So now we can do this for second order as well. So this is a first order solution here, or I should say first order IVP. So we can have a second order, which will require two initial conditions. So if you read the notes in if you read the book, you'll see that the initial conditions, the number of initial conditions that you need are determined by the order of your differential equation. Okay, so if we are order 1, we only need one initial condition. We are order 2, and we need two of them. Okay. Also, the initial condition will determine the interval of the solution once you solve for it. But anyway, let's try a second order type. So here is my differential equation. They're using the quote notation for some reason. Go ahead and use it. And they give me initial condition for the actual solution, x of pi over 2 equals -2. And the initial condition for the first derivative, x prime has pi over 2 equals to 1. So currently we're not solving any DEs yet. Well, we will very soon in chapter 2. But right now I'm just gonna give you the solution. So the solution x that satisfies this differential equation is going to be this guy. C1 cosine of 4t plus C2 sine of 4t. Okay. So in order to use the initial conditions, we're gonna have to take the first and second derivative, right? So we need to solve for C1 and C2. First derivative. Oh, we might not need the second actually. First derivative is gonna be what? Let's see here. Make this a little more exact here. It's be x of t, x prime of t. I mean, it's implied. It's not. You don't have to write it this way, but just because. Derivative of cosine. So what is the derivative of C1 cosine 4t? And this is stuff that you guys are pros at, right? What's the first derivative going to be for this first term? I might need more space. Yeah. So derivative of cosine is negative sine, right? But there's a chain rule involved, so it's going to be -4 C1 sine of 4t. Derivative of this guy will be cosine, so that'll be plus 4 C2 cosine of 4t. Okay. Are there any questions about the derivatives? Is that clear? Or is it weird? Okay. So now we will use the initial conditions to solve for C1 and C2. So let's try, I'm gonna try to separate this. I'm gonna do two pieces at the same time. X of pi over 2 is gonna give me C1, 4 times pi over 2, that's going to be 2 pi, right? Sine of 2 pi, well, that's going to be 0. This will be 1, so this gives me C1, which is equal to -2, right? Okay, so we use the initial condition for x, the solution, to get C1. Now we're going to do this guy to find C2. Any questions on how we found C1? Okay, so let me know at any time. All right, so pi over 2 of the first derivative is going to give us -4 C1, which we can plug in already at this point, sine of 2 pi plus 4 C2 cosine of 2 pi. So sine of 2 pi is 0, so we don't even need to plug in C1. So we're going to be left, we will be left with 4 C2 equal to, so equal to 1. So C2 is equal to 1/4. So now we have the particular, specific solution here. So I'll just plug it in. So x of t is equal to -2 cosine of 4t plus 1/4 sine of 4t. So this is our answer. It's 4, by the way. Any questions on this problem here?
I have a question.
That's your question.
So are we gonna be doing anything with that? What is it? X double prime plus 16x equals 0?
Eventually, you're going to use this to solve for x of t. So right now, I just gave it to you,
Okay,
and we did the initial value part. But yeah, when we get to chapter 2, you're going to be solving this yourself.
got it.
But that's the goal, is to solve a differential equation in this class, many different ways. You would be given something like this or something maybe more difficult, and you need to figure out what is the actual function that received these derivatives and satisfies this equation. We'll get there.
So we'll just be, my voice is off. I haven't talked in a while, I guess.
Very good.
But so we're just gonna be trying to go backward mainly.
Yeah, that's the whole point, because in real life, it's very easy to observe changes. So we can create differential equations, no problem. But solving them, finding the actual function is difficult, and that takes work.
For sure.
And the really complicated problems require computer solutions, numerical solutions. Okay. Okay. Let's do one more example and then I'll give you a theorem. And maybe one more after that before 1.2. You guys cool so far? Example 1 and 2 makes sense. So let me know if something doesn't make sense or whatever. Something you've missed something. It's not number 4. That's number 3. Each of the functions y equals 0 and y equal 1/16 x to the 4th satisfy the differential equation dy dx over dy over dx equal to xy to the 1/2. Okay. Oh, forgot something. And the initial condition. I'm going to just use IC for initial condition. Y of 0 equals 0. All right, so let me rewrite it prettier over here. So here, this differential has differential equation has 2 different solutions. So there's not. How should I word this? It doesn't have to be just one solution. There's usually always a trivial solution. Okay. This one being the trivial, y equals 0. Because if y is 0, it'd be 0 times x is equal to 0 because the derivative of 0 is still 0. So not interesting, but it satisfies it, right? This one is the interesting one. Because if you plug it in here, it will show you that it satisfies both sides. Right? Just for fun, let's go ahead and do that here. So if y is equal to 1/16 x to the 4th, y prime would be 4 or 1 over 4, right? So is that, if I were to plug it in here, so go ahead and show that here. If I plug in y and y prime, does it satisfy, right? Oops, I don't know why I did that. Should be x times the derivative, no, actually times the original to the 1/2. So is this equal? Square root would be 1/4. Square root of that would be 2. Yeah, it looks like it's the same, right? Y equals to 1/16 x to the 4 is a solution. So what this shows us is that an IVP can have several solutions. When we include y equal to 0. Okay. So without going too crazy into theory, we can confidently say that most differential equations will have solutions that how should I phrase this? We'll have solutions that are unique. That most initial value problems will have unique solutions, but it's not always the case in real life. Like in this book and in this homework, it will for the most part you're only going to see unique solutions, but uniqueness requires some restrictions on the problem. But stuff happens in real life. So, but anyway, let's go ahead and let's write down the theorem. To give you the conditions that will guarantee the existence and uniqueness of a first order solution. Let's try. 1.2.1 from your book is theorem of existence of a unique solution. Let R be a rectangular region in the XY plane. Defined by a less than equal to x less than equal to b and y is between C and D, that contains the point x naught y naught in its interior. If f of xy and partial f of partial y are continuous on R, then there exists some interval I0, which will be basically x naught minus h, comma x naught plus h, where h must be greater than 0. So I know it's a little wordy, but these are all the requirements to guarantee the existence of a unique solution. So all this is contained in AB, and a unique function y of x is defined on I0. That is a solution of the initial value problem. Okay. Let me give you a visual, because I know that's hard to grasp, without reading it many times. So in the book, what they're saying is, if you have a solution inside this region on this specific interval, then you create a actual unique solution. So if you have all the right restrictions, then yeah, it will be unique. That's all I'm saying.
So to be clear, existence and uniqueness are always paired together, or are there cases where one would exist and the other would not?
And for this theorem, it is paired together. So it exists. There is a unique solution that exists here, but only in that only under these conditions. Anyway, we'll slowly get deeper and deeper into this theories, but one moment. Should go to unpause that, but yeah, let me show you that thing in the end of the 1.2. This is really good remarks right before the exercises. That's I mean, I hope you read that through the section, but if not, just keep that in mind, that if the conditions are not met from this theorem, then you may not have unique, but you still could. could be nothing, could be several solutions. Are there any questions on 1.2? Okay. Have you guys started on 1.1 and 1.2 homework already? Okay. Let me look at 1.3 really quick. You guys have any questions on 1.1 homework or 1.2 homework?
I literally have only done like the first three. I'm probably gonna start on it more, but I mean, it'd be cool to just look at it. I'm honestly like taking like, it sucks because I'm taking like physics 2 and then linear algebra and all these math at once. I mean, I'm pretty good at math.
That sounds
So a
horrible.
lot of the things are similar and it's like confusing because certain teachers want certain things done a certain way. So I can't like use any shortcuts from anything else.
Yeah, it's true. That's
So
a rough semester, man.
yeah, it makes it confusing because I have to like do it a certain way for physics. And I'm like, I could just do it this way. And he's like, I want the units and everything. And I'm like, man, this stuff's so easy. If I could just do it the cheap way.
Yeah,
But not as more difficult.
no, it's true. The physics, I mean, the units matter, but it's a big deal in physics. It's true.
Yeah.
I know in math we don't really use it because everything is general.
Yeah, I would like to take a look at whatever.
Okay, let's see here. Well, let's look at. So you're on 1.1.
Yeah, I've only done like the first three, but I haven't like been able to like sit like do it completely. I just started on it a little bit because yeah.
Okay. Well, let's check it out. All right. So this is my solution set for homework 1. They're all randomly generated, so yours might be a little different. But let's just go through a few of them. So number 1, we talked about what does order mean, right? State the order of the given ODE. Well, order is dependent on the highest derivative. So we have a double prime, a single prime, and no prime. So 2 would be the order, right? No big deal. And then it says determine whether the equation is linear or nonlinear. And then they give you the definition here of a linear type. Notice how none of the y type variables or y derivatives have any kinds of power, or they're not inside of a function. So it has to be in this form. Now, if you look at the double prime, there is no power on it. There's no weird function. It's not inside of a function. It's just times an x, which is okay. So this doesn't mess it up. Although if you had times a y, that would mess it up. So this one is linear because it just has some numbers and x's, no big deal. If you would have had a cosine y over here or in there, then yeah, not linear. Okay. We did something similar like this in the notes. the highest order is 3. This has a power on the actual derivative. So when you see a power on anything that has to do with a y, or I should say the dependent variable, then nonlinear. But this is the same type of stuff. So let's see something different. Yeah, they're all very similar. No, is that do those ideas make sense?
No, yeah, those ones aren't really. I was probably more thinking about maybe these. I didn't even look at any of these yet. I don't know what.
Okay, these are a different type. Here it says verify that the indicated function is an explicit solution. So what you have to do is you take, so they give you the solution right here, and they want you to know, does it satisfy the differential equation? So you take a derivative, you plug it in here, plug in the original right there, and then you add it all up, and you should get 0. So if you do, then yeah, it satisfies it. So that's how you would show it on an exam. Like if I told you, does this thing satisfy this? You plug it in. Okay. On this homework though, they tell you to find the derivative. So derivative of this obviously is that guy. And then they ask you to let's see here. And here. Thus in terms of x. Oh, I see. And they just wrote it weird. So they want you to plug it in here, multiply by 3, and you're gonna get, so 3 times this is this piece. So they just want you to, so basically the stuff I was telling you to do on paper, they're having you do step by step. So plug this guy in here, take the derivative and plug that in there. And that's the simplification here. And then you add it all up and you get a 0. So that verifies it. So 8 is kind of weird because it's more of a paper problem, but they're trying to have you do it piece by piece. Does that make sense? Would you like to do this on paper?
You can see it. I feel like it's probably, it doesn't even look that difficult. I honestly don't like web assigned sometimes, but that's how it is.
Yeah, I try to delete some of the weird ones, but
That
I
one
guess,
isn't that bad. I don't like the multi-step ones. The multi-step ones get confusing.
yeah, those are the ones I got rid of. There was a ton of multi-step, but I'm still checking to see if I missed any weirdo problems. So if you see one that you think is ridiculous or just strange or messed up, just let me know and I'll just get rid of it. It's not a big deal.
Yeah, they're usually not even hard. It's just more the steps that they want you to put. It's hard to know exactly which one they want you to put in that spot.
Yeah, like it took me like a good minute to figure out what the heck do they want here. Like, what is this? You know, like the way they phrase it, I'm just like, I don't know what you're asking me. If I didn't have the answer in front of me, this would have taken me like probably 5-10 minutes to figure out what they're asking me. So I'm glad we talked about it. Number 9 is the same deal. Plug that guy into here, the y, take a derivative and plug that here. Add all the terms up, and you should get a 40 on the right side. So the left side should become 40. So that's all you're doing over and over again is verifying. Over here, this changes a little bit. Number 12. It says use a graphing utility to graph the explicit solution. So they give you the answer, which is right here again. Over here, it was a y, now it's a t, who cares? To graph this guy is what they want you to do. So I would just use Desmos or your graphing calculator, just plug it in there and pick the right graph. I don't care for doing this by hand. It's just kind of silly. It's unnecessary at this point. Yeah, graph this and you'll be good. Let's see here. Notice how they got rid of the E, because right now it's in terms of ln. So they introduced E to get rid of ln. I'm sorry, that's what I meant. Do you remember how to do that? The algebra steps? Okay, I'm assuming it's not a big deal. Okay. Well, let's look at, I guess let's look at 1.2 a little bit. EXM. Oh, okay. So here they give you a general solution for number 14. So they want you to figure out what is the value of M that will satisfy this. So try doing it in general, just leave it as an M, plug it in there, and then try to figure out, okay, what does M have to be in order to get 0? So this isn't too bad. So plug in Y equals M e to the mx, take a derivative and plug that in as well. That's all you got to do. So that'd be the same for all these right here. Okay, let's look at 1, 2. One point two is what we talked about today. So there you have to solve for C, right? So this is your solution to the differential equation. Plug in your initial condition, plug in 3, and then solve for C. You're gonna get whatever it is. Once you solve for it, find the domain of that function, and that's gonna go here. I didn't do any of these because, I mean, at this point, I assume you're able to find the domain, and if you struggle with domain, once you solve C, graph it, and just visualize the domain. That should be good enough. Or set the denominator to 0 and figure out what causes problems and exclude whatever causes division by 0, which will give you the domain anyway. Okay. Okay. So yeah, this is another one, just plug in the number, same type of deal. Number 3. Just find the solution. So once you do, you get this nonsense. Set this denominator to 0. And then you'll find you have 2 problem areas. You're going to have square root 3 and negative square root 3 that cause division by 0. So everything in between is cool. Everything after root 3 is cool. Everything before negative root 3 is cool. But root 3 and negative root 3 are not cool. Okay. Let me check one thing. 1 second. Yeah, I forgot one thing here. I'm sorry about this. So I thought this was asking for the domain of Y. This one was the domain of Y. This one's different. This one's the domain of the initial condition. So what is it? Give the largest interval I over which the solution is defined for the given initial condition. So basically, what is the biggest interval that contains the initial condition? Y equals negative 3. So it would have to be this piece, right? Because of these exclusions, separate intervals. Like over here, this domain would technically be similar to this, except replace all those numbers with √2. So you would pick the -1 here. Let's see if there's any more of those.
Excuse me, sir.
Mhm.
I don't see your screen.
Shoot. Thank you. Sorry about that. So what I was saying earlier, right here, I thought I was asking for the domain of y on this part on 3C. But 3B is asking for that. So over here, they don't ask for the domain of y. They just ask for the large interval where the solution is defined, solution of the IVP. So right here, we have multiple intervals. So I think you just need to choose the one that contains the actual initial value. So this guy. And over here you pick, if you were to solve this domain, you would pick this one. That's about it. So basically the biggest chunk that contains the input up until the first restriction. If there's no restrictions, then you just put all real numbers, right? Who cares? Doesn't matter. Does that make sense? Okay. Over here, it'll be similar to the problems we did. You're given a solution, C1 cosine, C2 sine, and you're given, since this is a second order, you're given 2 initial conditions. So you're going to solve it like we did in class. Same thing for 4, 5, 6, same type of deal. You guys have any questions on these types? Did it make sense in class? Okay. All right, does the homework seem doable?
I believe so.
All right, well, if you get stuck, let me know.
Yeah.
All
I'm
right.
like, I have a lot to do, but yeah, I'll try.
All right, man. Well, don't burn yourself out. I would never take 3 math intensive or science intensive at the same time, but good luck, man. That sounds, you're brave. I hope you don't have a job or anything, because that's gonna be rough.
Yeah, I'll be good.
So you just stop sleeping. I think that'll work.
I just write too much. Like I don't know. I can make my life easier, maybe.
Yeah,
I
just
write down a lot of stuff, so I feel like it like takes more time than it should. But
mhm.
I guess I learn it better.
Yeah, I mean, whatever works. I mean, I'd say just keep doing it, but I don't think you'll have much free time at all this semester.
Yeah, definitely.
All right, guys. Well, if you have no more questions, then we'll stop here. I'll let you know if about 1.3 later this week. For now, just do 1, 2, and 1, 1. I'm thinking of maybe just starting chapter 2 next time I see you. Perhaps this would be an extra credit section. Anyway, I'll let you know soon. If you guys have any questions, let me know. If not, I'll see you Monday.
Have a good day.
Thank you. Bye-bye.
Have a good night.
Have a good night.